Okay, good. Just moving the chair here. 1 second. All right. I apologize for the delay. My computer's getting old. It's causing me problems. So let me start talking about, first of all, exam 1. The score was, the average was much lower than I had anticipated, although this is a smaller group, so it's possible that you can have weird exam scores with a smaller group. When I compare this exam score with the Monday-Wednesday group, which is a bigger group, this was about 10 points lower. I had anticipated the average to be in the 70 to 75% range. Part of the reason was, for example, problem number 2 was basically problem number 5 in your web assigned homework. You would solve this, you'd solve both problems exactly the same way. You had 2 events that happened simultaneously in 1 frame. Okay, if you remember, I don't know if you remember the problem from the web assign, it's the one with the red and the blue light. So people had a hard time with that. And part B was really plugging numbers into an equation. Once you had part A, you just had to plug numbers into an equation for part B. Number 3A was plugging numbers into an equation. And I just noticed too many people had a hard time with that. So one of the recommendations I would make for you, and this is something I tell my students when they teach Physics A, when you are encountering new equations in physics, what you should do is write the equation down on an index card, explain what that equation is, and describe when it can be used and it can't be used. And you should have that equation in front of you, and all the equations in front of you, as you're working on the homework. Okay. When you write things down, your brain is processing that information. If you just read the book and just read what it tells you, you're really not processing as much as you would as if you were writing it. So it's good to write things out because it'll help your brain process. When can I use this equation? When can I not use the equation? And what situations, or what is this equation for? You should do that, okay? Because based on some of the things I noticed on the exam, it just seems like people did not understand the concepts. And I don't know how thoroughly people read the textbook either, okay? Because there's examples where the equations are being used, and you should go through them, read them, and understand them. Not only read them, but maybe as you read the problems, try solving them too. I mean, I tell you how to solve them. You just want to, again, when you write things down, it helps you to process things. Okay? When you're solving the homework problems, once you're completed with the problem, you need to go through in your head and think about what is the process that you use to solve the problem. What are the concepts that you use to solve the problem? If you just solve the problem and then say, okay, I'm done, and you go on to the next one, that's not going to help you. The purpose of the homework is to get you to go over the concepts that we're talking about in class and that you should be reading about in the textbook. Okay, so those are some ideas for you to help you do a little bit better on the next test. So I had expected the average to be between 70 and 75. The next test, the next unit, typically the average is between 60 and 65. So that's why I sent an email saying, okay, we have to work a little bit harder because the next unit is a little challenging. So the question is, what was the highest score in the exam? I think out of our group, it was in the upper 80s. And in the other group, I had a couple scores in the 90s. If I remember correctly. Okay. There's just too many low scores. That's the concern. Also, when you're solving problems, make sure you draw pictures. I saw a lot of folks who did not draw a picture of the scenario in the problem. So that's important too. And obviously, some problems don't require a picture, but some do. But If you draw a picture, it'll help you better understand what's going on in the problem. I will post a key soon. I was going to do it last night, but I wasn't able to get around to it. But I will post a key. In fact, what I'll do is I'll upload the key. Since you're not going to be back on campus until the 8th of October, I'll post a key online. But as we get later on, as we get through the semester, like in October, after October 29th, every Friday you're going to be here. And so the exam keys, I'm just going to post them in a glass case across from my office. Okay? Now, if you want to pick up your exams, they're here on campus. If you go to room S101D, our instructional assistant, Tyler, he has the exams. So you can just go pick it up there. And when you pick up the exam, please make sure I add up the points correctly. Because when I did your group's exams, it was about, when I finished, it was about 12:30 or 1 o'clock in the morning. So when you saw the email I sent you on Sunday, it was like really late on Sunday. Okay, so just double check I added up all the points correctly. I was trying desperately to get the exams graded so that you get something back right away. One of the advantages of doing the exam in person is that I have a hard copy. It's way easier to grade the hard copy of the exam as opposed to grading it on a computer, at least for me. Okay. Any questions regarding the exam? No questions? Because this exam is really worth half of the other ones, I'm not as concerned about this one as I would the other ones. Okay, I would be more concerned about the next 4 because they're worth twice the relativity exam. Okay, so I'd be more concerned. So I'm hoping that you guys put a lot of time in this next unit so you guys get it, so the average is better. Okay. No questions? Exam 2 is on October 8th. That's the next time we're going to meet on campus. And when you come on October 8th, I have to give you a multimeter, okay? Because you're 1 multimeter short in your lab kit. Your web assigned chapter 23 is due on the 19th, and there's also a worksheet called the electric field worksheet that's basically geared to help you to learn how to do the electric field calculations we discussed last Tuesday, where we take the object and we break it up and we determine our DQs, our R hats, and our squares. By the way, if you go in our modules, in the module for this unit, there are videos on this topic. I created a couple of videos on how to solve other problems. Okay, I created videos on how to solve other geometries. I did a disk. Okay, we did a ring in class. I did a disk video and put it on Canvas. So you might want to take, well, you should take a look at it. It used to be in the textbook, but it's not there anymore if I remember correctly. Okay, so take a look at the examples I've done for you. The more you see, the more you work on, the better you'll get at it. Of course, you've done these kind of problems in Physics 205 when you did gravity. Okay. Also, when you do the properties of charge lab, there's videos for you to watch. Please, in the module, go to the module, watch the videos. The Canvas, I'm using Canvas as a resource. You should be using Canvas as a resource for you. I'm putting videos there that you should be watching. I fully expect you to watch them. Okay, and especially when we go to circuits and you start building circuits, there are a bunch of funny videos about circuits. There's this one person who's online, he's an electrical engineer who makes these great videos on how circuits work. And you'll get familiar with him because I chose a lot of his videos. Okay, so please watch the videos in the modules because they're designed to help you to learn the material. Okay, and I try to choose some that were entertaining. Okay, so what I want to do today is continue discussion on the electric fields. I want to look at some kinematics and dynamics of particles in a static electric field. Static means that the electric field doesn't vary with time. So I should say a couple things about fields. We can describe fields as uniform. And we can describe them as constant. Can anybody tell me what the difference between those two is? Or are? What does it mean when an electric field is uniform?
Means it's the same all across it.
Yeah, this means it's the same value everywhere. What does it mean that it's constant?
It doesn't like change over time.
Yeah, this means time independent. So when we talk about fields, we generally say the field is constant, meaning it doesn't depend on time. But when we say it's uniform, then it has the same value everywhere in space or over a region of space. Okay, but when we say it's uniform and constant, that means it has the same value everywhere in space and it's time independent. Now, for us, the fields are static, so that means they're all going to be time independent, at least in this unit. Okay, in this unit, all the fields are time independent. It's not until we get to the last unit, or the second to last unit, where we talk about fields that vary with time. Okay? So, before I begin this presentation on particles and static fields, I want to talk about really calculating the field. I want to say one or two more things. Maybe I should write it like this. Remember, dq is how much charge is in your little element. R hat is the unit vector that goes from the source of the field to the point in which you're calculating the field. And R squared is the vector, the length of the vector that goes from the source to the point in which you're calculating the field. So here's a charge distribution, and here's a point P, and you want to calculate the field at this point. Okay? And I did objects that were linear, so I did, one-dimensional. So we talked about dq as some lambda times dx, or lambda times some arc length. And lambda is a charge per unit length. Well, what if you have a two-dimensional object? What if you have a disk? How do you write your dq for a disk? And there's an exercise in the homework where I make you go through this process so you understand how to figure out your dq, because this is one of the issues in solving these problems. Suppose I have a disk of charge. And I want to break up this disk into a piece small enough so that the field has the same value everywhere. In other words, I want to find the field at this point P. I want to break up that disk in such a way that the field over that little piece is the same everywhere. How do I break this up? Well, I can break it up in a little square. I can do that. The only problem is we haven't had Math 32, okay? I can't break that up into a little square unless you have Math 32. Because then I would end up doing a a two-dimensional integral, okay? But what I want to do is take into account some symmetry. Let's pretend that the charge density either is uniform, means it's the same everywhere, or it only depends on R. It only depends on how far you are away from the center. How can I break this up so that whatever piece I have can describe the electric field? In other words, let's say I break it up into a ring. Okay, and let's say I'm calculating the electric field out of the plane. Let's say right here. Okay, let's make it a little bit easier. It's true that from the tip of my marker all the way around the ring, the distance from the tip of the marker to any point on this ring is the same. And since the charge density is either constant or depends on R, that means however I break up that piece for that single value of R, I'm going to have the same charge on each of those pieces. And I'm going to break these up into pieces of equal length. Okay? And each piece then of equal length has the same charge in it, regardless of whether the charge density is uniform, or uniform I should say, or varies with R. Because if I'm out here, the distance is the same, my dq's are the same. Like the field is everywhere going to be the same all the way around here. So even if I make it, and I shouldn't say I said something wrong there. If I make this little piece and little piece, it's already an infinitesimal, so I screwed that up. Sorry about that. So that ring can be used to determine the electric field at this point where my marker is. So I can break it up into a bunch of rings. So I can break this ring up this disk into a bunch of rings. Calculate the electric field due to any one of those rings, and then add them up, or integrate. So then my dq would be the charge per unit area. If this was uniform, well, I'll just use sigma. So sigma is charge per unit area. And then I got to multiply by my area, which is the area of this ring. How do I find the area of that ring? Well, let's pretend I had a pair of scissors, and I was able to cut that out with a pair of scissors and straighten it out. This is infinitesimally thin, so the thickness is dr. If this radius is r, then the length of this piece is the circumference of that circle. And so my dA is 2 pi r dr. And so my dq then just imagine an old tree. Okay, if you had an old tree, it would have a lot of rings, and you can break up that cross section of that tree into just a bunch of little thin rings. And so that's all I did. By breaking this up into a bunch of thin rings, if I wanted to find a field where this marker is, I know that for this particular ring, the field at this point due to any part of this ring is going to be the same. The field's the same everywhere. Okay? If you go all the way around this ring, the field has the total contribution is the same. The field is going to be a particular value. I have broken this up into a piece small enough so that the field's constant at this point, uniform at this point. Okay, no matter where you are in this ring. Okay. That's the reason. That's why we're breaking these things up into pieces. You want to break it up into pieces small enough so that the field at this point, no matter where you are, is constant. And that's the case here.
And then we plugged the, was that sigma?
Yeah.
2 pi r dr into the dE equation.
Right. Then you put it into here. And then the r, I have to write an expression for the distance from here to here. I'm sorry, from here to the ring, which would probably be something like this, as actually that distance squared. And then you got to find your r hat. And then you're done. The video, I do a video on this problem, but my point is to how do you break the object up into infinitesimals? And then if it's 3 dimensions, really in this class, if it's 3 dimensions, really the only one we can do is a sphere. You could take a sphere and break it up into shells. You can break it up into spherical shells, like an onion, right? An onion has many layers, and each shell has a surface area. And so your dq for 3-dimensional object is going to be rho dv, where rho is the charge per unit of volume, and then your dv is the surface area of one of those spheres, one of those layers of the onions, and then times its thickness. And if you notice, if you integrate this, you get 4/3 pi r cubed. And notice if you integrate this, you get pi r squared. Okay. However, sigma might depend on r. I didn't put in what sigma is. Sigma could be constant, or sigma could be something that depends on r. I will not give you a charge density that depends on theta when you're dealing with a 2-dimensional object or a 3-dimensional object, because then you're going to be forced to doing a double or triple integral, which I'm not allowed to give you in this class. Okay?
Question. When you plugged in the dq that we found into the original equation, how did you get the 2 squared on the bottom? The 2 squared plus r squared?
Well, remember, you have to figure out what r squared is, right? So if you're out here, at the tip of where the marker is, from here to the ring, it's going to be the distance from the board to the ring squared, right? Let me see if I can draw this in 3D. You're up here, right? So you want this distance to the ring.
Yeah.
So that's going to be this distance z plus that distance r. And so you need to use a Pythagorean theorem.
Okay. Yeah, that makes sense.
So those are the kind of problems. So I do this problem in the video. I go through the entire problem, okay? So take a look at the video. And then the 3-dimensional ones, typically spheres, then you're going to use this for your setting up your dq. And a lot of the issues that we have on these problems is setting up your integrals. So I have a homework problem in chapter 23, I think it's number 9, where I have you go over setting up all your dq's. Okay? And I don't know if you, in Physics 205, if you did something called like a worksheet called the Distributed Mass Worksheet. I don't know if she assigned that. Okay, it's basically the same thing. Okay, so as you're going over the assignment, please don't hesitate to ask me questions. Okay, it's due on the 19th, the chapter 23 homework. And that problem, you got to know how to, you need to know how to solve number 9 in the homework, because a lot of your problems, and even on the exam, you're going to see problems like it. So you have to know how to do number 9. It's really important. It's going to be a key for you to be successful on the next exam. Okay, so now that we've talked a little bit about fields and we've done a little bit about how to calculate them. Of course, there's a lot more to knowing how to calculate fields. Okay. We're assuming, right, and we've been assuming the whole time that we're in a vacuum. Okay. And we will still continue assuming we're in a vacuum. Let's take a look at the motion of a charged particle in an electric field. So let's say we have an electric field E. And we have a charge in the electric field. So let's say we have a charge in an E field. There's nothing else interacting with the charge except for that electric field. So here's the charge, Q. And I want to know the force acting on it. Well, the force is Q times E. If I wanted to, I can draw a free body diagram, but then I'd have to know what Q is and what E is. Okay? But if the only force acting on the charge is that due to the electric field, then the total force, according to Newton's second law, is Q times E, and that's equal to ma. And so the acceleration is going to be Q E over m. If this was a gravitational field, this would be G. Okay? If this were a gravitational field, this would be mg. Or sorry, mg. And then A would be G. But we have an electric field, there's no m here, there's a q here, so you have q times E over m. And so this is the acceleration of a charged particle in an electric field. How the charged particle behaves depends on the electric field. Is the electric field uniform? Is it constant? Let's, for the sake of simplicity, assume that the field is both uniform and constant. What would that say about the acceleration of the particle? What would it say about the acceleration of the particle?
Would it be 0?
It won't be 0. All right, because I didn't say E is 0. I just said that the electric field is uniform and constant. It means it doesn't change. It means A is constant. If this number doesn't change, if this value doesn't change, should this value change? Let me just use a basic math, right? These Q and M are constant. So if this doesn't change, this shouldn't change at all. Isn't that true? The answer is yes.
Yeah.
Okay. And so that's no different than this problem where I drop this marker. Isn't the Earth's gravitational field near the surface of the Earth uniform and constant?
Yeah.
Isn't the acceleration constant?
Yep.
Same idea. Okay? Again, the math is the same. Maybe the physics is different, but the math is the same. If this is constant, this has to be constant. Okay? Remember, for gravity, what we had was this. Oops. The only difference is this letter's different. Okay? That's the only difference. If G is constant or E is constant, then A is constant. If I know A, how do I find V? Well, A is dV over dt. So then dV is Q E over M dt, and then V is the integral of dV I'm just doing kinematics, okay? Right, that's just kinematics right there. V is the integral of the acceleration. And then if I integrate the velocity, then I get the position, or the change in position. What about the work done on a particle in a field? Well, the definition of work is the integral of F dot dr. That's work, right? The integral of F dot dr. And if, let's pretend if E is uniform and constant, then it's just going to give you this. And according to work kinetic energy theorem, this is equal to the change in kinetic energy of the object. All right, the work kinetic energy theorem says that the work done by the net force equals the change in kinetic energy of the object. And yes, you have to remember this stuff from Physics 205. You can't forget it. Okay? You need to remember the work kinetic energy theorem. The field will do work on a charged particle, changing the kinetic energy of the charged particle. And I list there the mass of the proton, the mass of the electron. We've already talked about them. And then also now I'm going to introduce again a new unit for energy. Because we're dealing with small particles, protons, electron charged particles, the work done on these particles is going to be small. And so we define the electron volt as 1.602 times 10 to the minus 19 joules. And so a lot of times when we're dealing with small particles, we talk about the energy in joules. Now, people in atomic physics and physics in general use EV. I think chemists will write energy in terms of like joules per mole. There's so many different units for energy, which is not a good thing, but because we only work with one particle at a time, we define the joule, the EV. But chemists will work with a lot of particles at a time, so they talk about the energy like in joules per mole. Okay. So I want to do an example But before I do the example, I want to remind you of some kinematics. If we have a particle in an electric field that's uniform, we know that the acceleration is going to be constant. If the acceleration is constant, what's this integral going to give you? If you're integrating a constant, what you're going to get? You're going to get, if you integrate both
Just get the
sides.
variable.
I'm sorry?
You just get the variable, so it'd just be the velocity is time t times the equation.
Yeah. Right, that's the velocity. Of course, the velocity is dx dt, or I'm going to use dr dt, because I'm writing it as a vector. And if I want to find r, I got to integrate dr. When I integrate this, you did this in 205. Sorry for the bad erasures. All right, if I integrate, again, I'm integrating a constant. Well, actually here I'm integrating something that depends on t. I get t squared. What does that remind you of? Anybody? What does that remind you of, this equation?
It looks like just the normal equation, but with acceleration, where the QE over m is.
Yeah, that's it. This is motion at constant acceleration. That's all it is. And I'll tell you this, students, for some reason, when they do a problem for motion at constant acceleration with an electric field in it, they have a hard time with it. They have an easy time doing the motion in a gravitational field. When they change the g to this, people have a hard time with it. And you shouldn't. Right? It's the same equation, just the letter's different. So don't let that throw you off. I'll give you an example before I do this one. Suppose I have an electric field that points straight down. Okay? Suppose I have an electric field that points straight down. And I send in a positively charged particle moving to the right with some speed v. What's going to happen to that thing as it enters this region?
It's going to go down.
So it's going to do this, right? What shape is the trajectory going to be?
Kind of like an inverse exponential.
Not an exponential. This is not an exponential, right?
True. Oh, just a parabola.
It's a parabola. It's an upside down parabola. That's no different than if I took this object and I threw it across the room. Right? That's exactly the same problem. From a physics point of view, it's the same problem. From a problem-solving point of view, it's the same problem. The letters are different, But it's the same problem. And so one of the things you have to learn as you're learning physics is that whether we have a charged particle moving in the electric field pointing downward like that, positively charged particle, or I throw this object across the room with a horizontal initial velocity, it's the same problem. It's the same trajectory. Same equations are being used. There's nothing different. Okay, if you see them as a different problem, then there's a conceptual understanding there's a problem with the conceptual understanding between the gravitational field and electric field, because from a mathematical point of view, they're the same thing. Okay, you have a constant field. So let's do this problem that you see on the screen. We have a particle, and you're given the mass. So let me erase the board, because I'm going to need board space. And by the way, in the homework, there are a couple of problems like this. You need to understand how to solve them. Because really, it should be a physics, to you, it should be a physics 205 problem. Just the acceleration, the source of the acceleration is different. But the equations are the same. So the particle of mass, m equals 1.2 times 10 to the minus 8 kilograms, and a charge of 1.0 millicoulombs. Okay, let me check my notation. Okay, and it has a velocity. This is the initial velocity. (3.00 minus 5.00 j times 10 to the third, it's going fast, meters per second. And it enters a uniform and really constant electric field minus 6.00 I plus 2.00 j times 10 to the fourth newtons per coulomb. And I want to know the acceleration. Okay, I want to know A. Well, we just showed that A is Q E over M. I'm going to take minus 1.0 times 10 to the minus 3 coulombs times the field divided by the mass. And then you just punch this in on your calculator, and that will look up my answer. And that's a very high acceleration, but these are small particles in a strong field. They're going to experience a large acceleration. Okay. So that's the acceleration of the object. I want to know the velocity after 3 seconds. Okay, I want to know the velocity next after 3 seconds. So I need to use my kinematic equation for constant acceleration. That's my kinematic equation for constant acceleration, where A is QE over M. So now it's just a plug and chug problem, right? Because V naught and I'm going to have to erase the board up here because I need my space. All right, so when you bring that all together, you can do this on your calculator. You'll get the following. I guess the speed didn't change that much in 3 seconds. Oops, it wasn't 3 seconds, it was 3 microseconds, sorry. Okay, sorry about that, it's 3 microseconds. Now, how do you find the displacement? Again, I'm going to use the kinematic equation. By the way, you have a homework problem just like this in the web assign. It's to review kinematics. And everything's written in unit vector notation. Because I think that's what you did a lot of in 205, right? Okay, so now I want to find the displacement. So I'm going to take this thing and multiply by time. Please let me know if there's anything you question. There's a lot of writing for me. And then you punch all this in on your calculator, and you'll get I'll get out of the way here. That for my change in position, my displacement. Questions on that? From a point of view of the kinematics, this shouldn't be anything new to you. The only thing that's going to be new to you is that the value of A, the source of the A, is different. Okay? That should be the only thing that's new to you. Otherwise, these problems should not, unless you struggle doing kinematics problems in 205, this shouldn't be that bad a problem. Of course, this actually helps you to reinforce what you learn in 205. So it actually should help you become better at it. Okay? So there's a couple of problems in the homework on the kinematics of charged particles in electric fields. And also on some of the dynamics. What's the change in kinetic energy? Okay. All right, the work done equals the change in kinetic energy. I could have asked that question too, but I didn't. Okay, but that one shouldn't be hard because I can calculate the change in kinetic energy several ways because it started with this velocity and it ended with this velocity. So I just need to know 1/2 mv final squared minus mv initial squared. Or I can calculate the mass times the acceleration times the dot product with delta r. I should get the same result because the work done by the net force equals the change in kinetic energy. All right, so I want to introduce to you another topic. So now we're going to get a little bit abstract. Okay, and really this is the beginning of chapter 24. Now remember that the direction of the field that we described we did it by taking a test charge and bringing it in the vicinity of a source charge. I did that long thing last Tuesday, okay? And really investigating the force on a test charge. And then we took the force on a test charge and divided by the value of the test charge, and that allowed us to define a unique vector everywhere in space. So let me draw a positive point charge. And my board here is going to be my space, okay, two-dimensional space. But this applies to 3D space also. So here's a point charge. It's positive. And what I can do, when I put this thing here, it distorts space, because what happens is if I bring another charge near it, it's going to experience a force. But I know that the field due to that charge is always going to be away from that charge. So if I'm at a location in space here, and a location in space here, and a location in space here, I can really write a vector, assign a vector, a unique vector here that represents the electric field at this point due to that charge. It's going to point away from it. It's going to go like that. Now, what about here? I can also assign a unique vector. Unique meaning there's only one vector you can assign at that location. Okay, those are called vector fields if you've had Calc 3. Now, what can you say about the vector over here? Well, you're going to be further away, so the vector should be shorter. But it's going to point in the same direction, and this vector will be even shorter and point in the same direction. I can do that everywhere on the board. I can assign a unique vector everywhere on the board. And each one of those arrows represents what the field will be at that location. The length will tell you how strong it is, and the direction will tell you what direction of the field is going to be. And you see that in that picture. You go all the way around and do this. In fact, you can do the same thing if you take a positive and negative charge. And you can do the same thing. You can actually assign a vector everywhere in space that represents the field at that location. And you see that in that picture. That's called a dipole, right? Because you have a positive and negative charge that have the same value. Now, if we connect these vectors with tangent lines, so let me go back to the previous slide. If we can connect the vectors, all those field vectors, with tangent lines, then this will say something about the electric field. We're actually mapping the electric field produced by the source charge. And these are called field lines or lines of force. Any lines drawn tangent to these field lines represent the direction of the electric field at that location. So if I connect these with tangent lines, this is called electric field line. And what I can do then is draw go to this point and draw a tangent line here, and that's going to tell me the direction of the field at that location. And we can say something about the size of it in a little bit. So there's the electric field lines due to a positive charged particle that you see in the slide. Okay, the yellow lines. So if I go back 2 slides, 3 slides, this is what I had originally. And so what I did is I connected them with tangent lines. These are the field lines. The yellow line represent what the electric field would be. So if you put a charged particle on one of those yellow lines, if you put a positively charged particle on one of those yellow lines, that arrow is going to tell you which direction that positively charged particle will move. The idea of the field line was introduced by Michael Faraday. This is a very abstract concept. And there's a lot to this. Michael Faraday wanted a way to picture fields. Okay, he was very good in the lab. He wasn't as good in math as he was in the lab. And so he wanted a way to picture fields. And so he came up with this idea of field lines. So let me draw the field lines for this positively charged particle. Remember, this is representative of the field center. You know, how many I draw is arbitrary. I know that the field is going to point away from the charged particle. And this thing just tells you the direction of the field. I'm drawing a bunch of them. Like that. Now, what do we notice about these fields? These field lines. If you get closer to the charge, what can you say about the spacing between those lines? Or what can you say about how close they are? In other words, suppose I drew, just for fun, I drew a circle around this. And let me use a marker that works. I'm going to draw 2 circles. So those are 2 circles, or in 3D they would be spheres. What do you notice about the number of lines that go through those 2 circles?
The same number of lines.
The same number of lines go through them. But what about the density of lines here as opposed to the density of lines here?
I mean, the distance between them gets bigger as it goes out.
Right.
As it goes away from the center.
So the density of lines here is greater than here, correct?
Yeah.
The number of lines penetrating this surface is, the number of lines per unit area penetrating this surface is greater than those penetrating this surface. And that's true. And there's a reason for that. Because you're closer. If you're closer, the field's bigger. Isn't that true?
Yes.
So we can say then that the number of lines passing through an area, okay, a surface area perpendicular to lines is proportional to the size of the field. The density of lines tells you how strong the field is. So what this tells me is that since the density of lines here is more than here, then the field here is greater than the field here. So it's giving me some qualitative information. The density of lines passing through this imaginary surface is greater than the density of lines passing through this imaginary surface. So that says that the field, you know, as you get closer, is greater. Closely spaced field lines mean large electric field. Sparsely spaced field lines mean small electric field. Now, field lines will either go towards a negatively charged particle or away from a positively charged particle. If this was negatively charged, the arrows will point the other direction. The arrows will go into the surface instead of out of the surface. So if we want to draw field lines to represent an electric field, we need to think of a couple of things. Number one, the number of field lines entering or leaving the charge is proportional to the charge. So if I had something here that's 2Q, if I drew 10 lines around here, I'd have to draw 20 lines on that one because that's going to represent the fact that I have twice the amount of charge. And of course, that's going to mean twice the field at the same distance. And I didn't draw this very well, but when you draw the field lines, you should draw them symmetrically around the charge. I didn't do that. Another thing to remember is that the field lines either begin or end on the charges, or they go to infinity. They either begin or end on a charge, or they go to infinity. Because if you notice here, they start at the charge and they go to infinity. If this was a negative charge, then it would come from infinity and go towards the charge. And you can't have field lines that cross. Field lines cannot cross each other. That's an important rule. And everybody has a hard time with that one. Why can't field lines cross?
Wouldn't that mean it's going in two different directions?
You're absolutely correct. Right? You're absolutely correct. It means that you'd have a location in space where the field has two different directions. That's not unique, right?
Mm-hmm.
Right? When we have an electric field, we should be able to define a unique vector everywhere in space. So they can't cross. And you're right, I wouldn't have a unique direction then. If I have a positively charged particle near, let's say if I had these two, let's make this negative. The sum of the two fields is going to give me a direction of a field line, and that's at one direction. So you draw the sum of the two fields. You don't draw each individual one. Okay.
Sorry, you say that one more time, that last part.
So I know, for example, the field lines due to this charge go like this, right?
Yeah, into it, right?
Yeah, but then, obviously I can have one that goes like this. But I don't draw these individual ones. I draw the sum of the two.
Like a full line.
Yeah, whatever, the sum of these two, whatever that comes out to be, if it comes out this way. I don't draw the individual ones.
Yeah.
I draw the resultant vector. And the resultant vector goes in one direction.
Okay.
Okay, because that way I can assign a unique vector at that location in space.
That makes sense. Okay.
So the picture I have, and maybe let me make the picture bigger. Oops, sorry, I'm so close. I gotta find where the mouse is. So that picture, basically 2 point charges, they're really 2 small conductors, in oil. And there's thread in the oil. So we charge the conductors, and the thread forms the field lines. This is taken out of a textbook. What can you say about the sign of the 2 charges?
They look like they're negative.
Well, they're both the same charge. It's hard to tell.
Yeah.
Yeah, they're both the same charge, right? Because you notice in the middle, the field lines they don't come together, right? They actually
don't really
avoid each other.
even exist there. They're just kind of repelled by each other. Like
Yeah.
putting 2 magnets at each other.
So basically, they're the same charge.
Yeah.
Okay, and they're equal charges because it looks like, you know, you have the same density of lines coming through from each one of them. These are opposite charges. This is the dipole that I showed you earlier. All right, this is the nature draws them this way. Okay, the strings actually form that pattern when you make one positive and one negative. Those are the field lines of a dipole. If one of them had twice the charge, then you would see that one of them would have twice as many lines coming off of it. I'll show you this video. I probably shouldn't be showing this because I'm going to be putting this on YouTube, but hopefully, I don't know if this will work. Let's try it.
To the ground attachment of a Van de Graaff generator, we connect a large conducting sphere. When we turn the generator on, the generator's sphere becomes strongly positive in charge, and the other becomes strongly negative. We sprinkle bits of fur into the air around the spheres. A very distinct, stable pattern appears. This pattern indicates an electric field. Notice that the field is not quite symmetrical. This is caused by the presence of other conductors, such as people, in the vicinity of the spheres.
Okay, so that gives you an idea of what the field lines look like. So this video, when you watch if you watch this video on Confer Zoom, you'll be able to see it. But when I put this on YouTube, I have to blur it out. Okay, just because of copyright issues.
To the ground.
Oops. Okay, so let's say a couple more things about the field lines. Okay. Let's go, let me redraw this picture, okay? So here's my positive charge. And I'll draw my field lines. It's hard for me to draw things symmetrically. I'll try. Okay, those are the field lines for this positively charged particle. By the way, it's a good idea to learn how to draw these fields. But with WebAssign, it's actually hard to do assignments where you're given an exercise where you have to draw the field lines. It's actually kind of hard to do that. You might be asked the question in an exam, what do the field lines look like? Okay. Go over the examples in the book, and as you go through the examples, kind of try to draw them out yourself so that you can process how they're drawn. I want to consider the electric field at 2 points in space. Okay. We said that the number of lines per unit area is proportional to the electric field. The density of lines is proportional to the electric field. Let's look at the electric field at this location. Here. And so we'll call this R1. And let's look at the electric field at R2. By the way, because of the point charge, isn't it true that the electric field, anywhere I draw on this imaginary surface, is the same value? Because Remember the electric field for a point charge.
Wouldn't the radius be the same from the point charge to the spot?
Yeah, that's right. All right, because of that symmetry, anywhere along that sphere. So I'm trying to use a simple example. Okay, so the electric field E1 E1 is K Q over By the way, I'm going to write K a different way. Because remember, we wrote K as 1 over 4 pi epsilon naught. And electric field at location 2, so I'll write it in terms of epsilon naught. All right, so let's take a look at the ratio between E2 and E1. When you simplify this, the ratio of these goes as 1 over the ratio of the surface areas. Aren't these surface areas?
Isn't that just the area of the ring, or that's the circumference?
No, that's the surface area of a sphere.
Okay, yeah.
Okay, this is so the ratio of the fields goes as 1 over the. It goes as 1 over the ratio of the surface areas. So what does that tell you? That the ratio of the fields, the field depends on the number of lines per unit area. You can see that very clearly. Okay? This easily shows you that the strength of the field another way to look at it is consider the number of lines per unit area going through here. And then the number of lines per unit area going through the second one. So let's look at the ratio of number of lines per unit area. So let's do this one first. By the way, both of them have the same number of lines per unit area going through it, right? I'm sorry, both of them have the same number of lines going through it, right?
Yes.
Okay, so the number of lines per unit area going through each one is going to be and I'm going to do the ratio of the second one to the first one. When you do this ratio, it's going to match the ratio of the electric fields. Again, a strong indication that the electric field is proportional to the number of lines per unit area passing through some sort of imaginary surface. And we got to be careful. It's got to be the number of lines per unit area passing perpendicularly through here, because if you have an arrow that has a component parallel to the area, it ain't going to go through, right? Just like if you have water flowing through a pipe, if the water is flowing like this, it's only the component perpendicular to the area that's going to go through the pipe, right? And so this also agrees with Coulomb's law, too.
Hey, Professor.
Yeah.
On the ratio you did with the ends, shouldn't it be R2 on the bottom?
Well, I did the ratio of the second one to the first one.
Oh, okay. All right.
And then when I simplify this, then I'm going to get...
I see it now. Yep.
Okay.
I think your screen is frozen, though. I'm not seeing you move.
Okay, hold
There
on
it
a
is.
second.
All right.
Am I
Let's try
frozen?
it again. You're good. Yeah.
I'm moving now?
Yeah.
Okay, because I
It
can't...
just froze for a second. Yeah.
Oh, it does look frozen. Okay, no, I'm okay, okay.
Yeah, you're good. You're just off screen.
Okay, good. My computer's acting weird, so I have to look at... I don't know, it's just bizarre. I can't get my camera software and Zoom on the same screen. It's just weird. Okay, let's look at the product of the electric field times the area. Because if the number of lines per unit area is proportional to E, then E times the area is proportional to the number of lines. Let's take a look at this. By the way, this is going to be very important. What I'm going to do now is very important. I'm going to show you this for this case, but it turns out it's true in general. And I'm not going to prove it in general, because you need Calc 3. So let's look at the electric field at this point, right here, okay, on this imaginary surface. The electric field there, let me use a different marker. It's getting bad.
This is using R1, right?
I'm just going to use R1.
Okay.
And I can do the same thing for, I mean, it's the same argument for R2, so it doesn't matter. So E1 is K. I'll go back to K if you don't mind. But actually, no, I'll use 1 over 4 pi epsilon naught. Four pi epsilon naught times R1 squared. And I'm going to multiply by the area. And now I'm going to be able to do this very easily because the electric field has the same value all the way around. If the electric field didn't have the same value all the way around, I'd have to break up this field, the surface, into teeny tiny pieces, small enough so the field is constant over that piece. And then I'd have to integrate over the whole thing. But I chose this example because it's making our life easier. So I'm going to do Q over 4 pi epsilon naught R1 squared. And now I'm going to multiply by this surface area, which is going to be 4 pi R1 squared. And you're going to get a lot of cancellation. And you're going to get whatever charge is enclosed over 4 over epsilon naught. And in fact, I don't have to do this with the absolute value sign. I can do it this way because, and you'll see why later, this integral is going to involve the electric field, the dot product of the electric field, and something related to the area. So actually, in reality, I don't have to put an absolute value there. And you'll see why later. So the number of lines passing through a closed area, and this is an imaginary sphere, right? I just drew an imaginary sphere, is whatever charge is enclosed inside that sphere divided by epsilon naught. Notice that the integral is independent of the size of my imaginary surface. What if I did R2? What if I did this big one?
It'd have the same result.
I get the same result. That's important. In fact, it turns out it's true in general. Even if the field is not constant over the surface, it's true in general. Okay? This product is called the electric flux. Okay, that product is called the electric flux. And so I realize that it's almost 12:30. I'm going to stop here. And then we'll come back after lunch, okay?
Okay.
And